So I'm a little bit curious. Who here is interested? Can you guys hear me?
Yeah.
Okay, that's my first curiosity. Secondly, who is interested in developing, like adding new functions to Stan? Show of hands, maybe? Cool, a lot of people, that's good. How about changing the Stan language syntax? Cool, we have some other people, like 4 or 5 people. Sweet, okay, we'll do a bit of both, but we're gonna focus mostly on the adding a function part. But there will be some slides on like basic compiler structure. Okay. So, first things first.
The main people working on the language are me and Sean and Mitzi, who's back there, and Matthias, who we just hired, who's floating around somewhere.
He went to a different one because he already knows all this.
Yeah, you can ask Mitzi questions. She already knows all this too.
Right, so first up, there's some documentation online. A lot of this material in the slides kind of came from these wikis, and the wikis usually have more detailed information. We have different repos for different parts of it, so they're split up a bit, but that's mostly for later. So, yeah, here, when it says we, it means Bob and someone else. Someone asked Bob what the best and worst decisions he made about Stan were, and he was saying the worst was that he chose C++ and also the best. And there's...
It was not my choice alone.
Yeah, sorry. There's a bunch of reasons. I'm not going to read them all. Essentially, to summarize, C++ lets you do a lot of computation at compile time, even if it's a bit hairy looking. And it also has one of the best matrix libraries out there, so we don't have to do a lot of that work. And that, I think, together counts for the majority of it. It also makes it a little bit easier than other languages to do your own memory arena. So these are like very high performance considerations, which is helpful when your model might run for a week. So why not? It's a bit hairy, it's a bit difficult, especially C++ before C++ 11. We recently switched over in Stan, but we haven't converted all of our code to the new format or the new like style yet. Yeah, it's dangerous. It's very easy to shoot yourself in the foot. And compile times are quite high. I think models are like 30 seconds-ish. Although we're working on that, so there's ways to mitigate that. And feel free to interrupt me if you guys have questions along the way. Right, so now I'm going to try and go through kind of the whole Stan architecture from when you're writing a model to what actually happens on the computer. So first you write it in the Stan language, and then the Stan compiler translates that into a C++ model class. That model class includes and inherits from, or doesn't inherit, it includes the math library and relies on all the functionality that's in there. So most of the things that you're actually referring to in a Stan program are in the math library. That model class is then compiled in a single translation unit with all those includes from the math library and also some algorithms and services and stuff like that. We're hoping to switch to multiple translation units later for compile time reasons. And then that result either with command Stan is compiled with like a main function and some command line parsing and stuff like that, or it's linked in to a running rstan or pystan interpreter. Right, so the model class we talked about has a fixed concept. It has like a few methods and maybe fields, just methods, that are relied on by all of the other things that touch it. Yeah. That model gets constructed with data. So when you declare data in a Stan program, that gets read once in the model constructor and then saved as part of an instance of the model class, and then used over and over again later. It implements a function. We'll talk more about that in a second. I won't read this. So the log prop method is the sort of main entry point that you are probably thinking about. That applies to a vector of unconstrained parameters. So those are the arguments to the function, to the method. And then it returns the log posterior up to some constant. It's coded as a joint density, or this other thing that people don't use that much. And I guess the key a point here that might be good to take away is that the log prob function is operating on the constrained space. So when you declare that a parameter is lower or equals 0 or something like that, you're saying you want it to only be positive. So by the time your model executes, it will have a positive parameter when your code evaluates. So that's what's happening in that log prob method. But under the hood, there's things going on such that the sampler, HMC, or whatever, is operating actually on the unconstrained real line for that parameter, and then sort of automatically doing the constraint back and forth where appropriate, and doing the log Jacobian as necessary. Yeah. So then there's also some other methods that you can write in a stand program, like transform parameters and generated quantities. These have representations in the model class as well. Yeah, the thing that translates is sometimes called the compiler or the parser or the transpiler, depending on who you're talking to, or stan-C, if you don't want to get into a terminology debate. It's written in C++. All the code lives in the stan repo under lang. Other things that live in the stan repo include the inference algorithms, services, and memory directories. Yeah, so there's kind of three parts to the transpiler. There's the parser, the thing that actually reads the syntax, and then it will construct an AST, which is mostly a bunch of data types. And then that AST is fed to the generator, which produces C++ code, the model that we were talking about earlier. So most of the stand functions that you see are actually direct, like direct references to math library functions. Those functions can use the math library's autodiff, or you can define your own gradients analytically. We try to do the latter as much as possible. Then they get exposed in the stand language fairly simply. There's just a file that you edit where you tell the stand compiler which function signatures are allowed for this math function. Then, right, I kind of covered this. So I guess the interesting thing here is that it's all compiled header only. I kind of mentioned this before. So that means what's happening behind the scenes is this generative model C++ class and the math library and the algorithms are all pasted into essentially the same file by the C++ compiler and then compiled all at once, which is huge. That's in C++ terminology, that's called a translation unit. There's some weird things that happen as a result of this, where we have to declare all of our functions in the math library inline. Well, that's actually so they work with different translation units, I guess. But yeah, so that has some consequences. Right, there's all these other things included. Oh, right, and there are some exceptions to this. So there are some libraries that we use. MPI and GPU are both for sort of parallel computation. They have frameworks that are external and that we link against binaries from them. The Sundials library that has ODE solvers as well. There are a bunch of different interfaces to Stan. We're going to concentrate on command Stan because it's kind of the thinnest and easiest to develop on Stan itself with. They all implement callbacks for the different kinds of ways they would like to interact with the Stan program. Right, so all of the code lives under the StanDev organization. The way that we typically think about it, command Stan's kind of at the top of this, and then it has a bunch of Git submodules for the rest of the code. So the main one in command Stan is for Stan, sorry. That Stan then includes math under libstanmath. Right, so from command stan's perspective, math is at stan lib stanmath, and then actual source code is even further down. There's other libraries in the math lib where we've kind of copied them in. Oh yeah, Boost, some of Boost, not all of Boost, Eigen, Sundials, OpenCL, Google Test. Yeah.
The relevance of that is that you can use functions from these libraries in your C++ code.
Yeah.
Other than syntax.
Right. Sometimes you can use them. Like, we tried to use the Boost file system API, which was in our header thing, but was not being linked to yet. So there can be intermediate steps. But these libraries are all of the source code that we care about is copied into the Stan repo itself. So there's no submodules or whatever there. It just comes every time you clone. Right, so what is a Stan program? Like, what actually gets compiled when you make a model with command Stan? Essentially, the Stan program takes in some data that you provide to it, and then it returns a bunch of parameter draws that are typical for that data. So this is using the model under the hood, and that model also takes in this data, and then it's paired with an algorithm that runs the model log prob block many times and uses magic HMC in order to get typical draws from what that model suggests is your posterior density. Right. So most of the complexity in a Stan program is actually in the likelihood, or in the joint density in log prob. I should fix that. Thanks. And all of that is defined by you in the Stan program using functions in the math library. I'm going to stop for a second. People have questions so far? I see people thinking, which is good. Okay.
What is matrix program? I mean, what is that program supposed to be? When you say
This is not a real signature. This is my simplified version of it.
Like, this is supposed to be a function in the Stan language?
This is supposed to be how you should think about what your model and algorithm are compiled together to give you. It essentially gives you something like this interface. It doesn't really. There's no C++ equivalent to this. But that's the way that I think about it, is it gives you a program where you feed it data and it feeds you draws. Right, so most of the actual code in Stan is also in the math library. There's a bunch of different functions. There's autodiff. So the math library has a very bounteous garden of forking paths. It's first split into Stan and test. They are supposed to be parallel. They are almost parallel. The Stan directory is also split into math first. And then they're both split into scalar and mat, which is supposed to indicate if you are using standard vector for R or eigenmatrices and standard vectors for mat. But we actually don't need that distinction, so we're going to collapse it at some point when someone gets time. Then further split by functionality. This is a bit looser. Where's the...
I think we're missing...
Yeah, I think there was a merged conflict. We missed a line. The first split is not on here. It's actually by autodiff variable type. So it's by prim, rev, forward, or mix. So we have primitive stuff that doesn't have any notion of autodiff. It might be usable from an autodiff library. We have a reverse mode autodiff, which is our kind of main workhorse. Then we have forward mode, which I don't think we use, and we have mix, which is a mix of forward and reverse, which we would eventually like to use once it's tested for things like Riemannian HMC to do second and third order derivatives with autodiff. But that stuff is there, but it's not really, forward and mix are not really used that much. Right, so there's the reverse mode, there's the autodiff level split, there's the container level split, which is going away, and then there's the kind of functionality level split, which is, so there's error functions, there's things that are fun, there's meta programs, there's probability distributions. So these live very deep from command stand's perspective. Let that sink in for a second. Yeah. So for testing, we use Google Tests. It's fairly simple, test endin underscore test.cpp. There's a bunch of macros that it defines. We mostly use test and expect equals, or expect. Test directory structures parallel. There's a run test.py helper script, which should be your kind of entry point to tests. And we will run a bunch of the tests. We will run all of the tests in various different ways on Jenkins whenever you submit a pull request. Here's the URL. The Jenkins stuff.
People should feel free to ask if you don't, like, how many people here know, like, continuous integration in this whole process? Like, does this make sense? Is there anybody where this doesn't make sense, like, doesn't know what? Feel free to say. We're here to, like, help. Okay.
The idea behind it is just in case there's shy people, the idea behind it is that we want to run tests on your code when you're submitting it for us to examine, sort of to make sure that it passes all the tests and makes sense. And then we also would like to keep our develop branch sort of clean and operational for everyone else so no one's running into unexpected test failures. Yeah?
Do you have a code coverage belief, or like, can you submit things that aren't 100% code coverage? Or
We do not have automated code coverage, nor, do you say a belief?
Well, can I submit a PR that's not 100% tested? I would say no, but...
So we sort of, what do you call it? Socially, we will enforce that we think it's mostly tested. There is no automated tool that checks this. Yeah, we've had trouble historically setting up code coverage stuff, but that would be great if someone knew how to do that and could make it work.
Do you know anything about C++?
Yeah, cool. I was kind of hoping I was going to learn something.
I mean, there are tools and startups around this. They're just non-trivial. So I think like our kind of makefile situation is a bit non-standard, so it's hard for these coverage tools to interact with it, especially because our math library is header only. So I guess we could do coverage for tests, but anyway. So the other nice thing about Jenkins right now, which is the thing that runs the tests every time we submit, is that the code that actually runs the test lives in the repo as well in this Jenkins file at the top level. So if you're ever wondering, like, how did, my test failed on Linux unit with MPI, like, how does that run? You can go look in this file and it'll tell you exactly the steps that are run. Right now, it doesn't really tell you the libraries that are required in that file. Eventually, we might move to Dockerized Jenkins, where that would also be kind of in there.
So there's one Jenkins file per repo.
Yes. There's one of these files per repo.
It's easy to overlook.
Yeah, we test a certain amount of OSs and tool chains that are in this wiki. Right. Any questions on part 2? Other questions? Okay. So this is the process that we hope people go through when they are considering contributing to Stan. Sort of every time they're considering making a contribution, so and us too. So if there's a larger change where you want to refactor a large amount of code, or you're proposing adding like a major new subsystem or something like that, that'd be great if that went through some kind of like design review. We're working on a design review process, but informally, a discourse post is a great place to start, kind of discussing it with other developers to see if the idea makes sense to them, if the design looks good, and eventually you'll want to get some kind of like stamp of approval from somebody that says like, this is a good design before you start coding. And that's mostly just for larger kind of major refactorings. There's one example where there's like this IO subsystem refactor that has gone through like a couple of different iterations on discourse. After that, you'll want to make a GitHub issue describing the problem and like sort of how you think you will solve it, with a technical solution and a functional specification. And this functional spec is more about how the clients of whatever you're building will see change. So right, then you'll code the solution somewhere. I think this should say on your fork, but branches are fine if you have access to the main repo. You'll create a pull request. The pull request has its own little template of sort of steps to follow. The most important one of those, I guess, is the license, where you kind of sign your name or your company's name that you're submitting this under a BSD license. Yeah, there's a code review process using GitHub pull requests, and there will probably be changes requested, so you'll kind of iterate a bit. And then after the test pass, you can, and someone approves it, you can go ahead and merge, or someone else will merge it. So who here has GitHub set up, has an account? Okay, great. Who here has forked another repo before? Who here has thought about it and was curious why you would do that? Okay, no one is curious, good. So setting up SSH keys I find very pleasing, but you don't have to do it. There's a link here if you're interested. It basically lets your computer automatically log into your GitHub account every time you push and pull. So the first, you'll want to fork the repositories that you care about editing from the StanDev organization to your own organization, and then you'll clone the command stan repo recursively. Either your fork or the normal StanDev one if you haven't forked it. The recursive part is important. It gets all the submodules like stan and math. Then you'll add a fork on whichever, your fork has a remote on whichever repo you care about. So some pictures going through. This is the way to clone something from GitHub. I think you guys are familiar. The fork button's up in the top right. Once you do that, you'll get your own fork of it here. And then the adding a remote part is a bit confusing. Who here knows GitHub remotes, or sorry, Git remotes pretty well? Not many people. Okay, so half. So a remote, normally when you do a Git clone, you get one remote, which is the origin that you cloned from. And when you push or pull, the kind of default is to go back to that origin. In our case, our origin will be StanDev, but we will also want to push and pull from another organization's copy of this repository, which is your own. So you'll add yourself as another remote, and then you can do git pull Sean master or Sean developer, whatever. That's my name. But yeah, so that's what the commands here do. You can name it whatever you like, and just make sure that this part is pointing to your actual remote. The name will be different for you. Do you have a question?
I'm always confused by Git, so yes, I would have a question if I needed to do this myself. What is Sean? Is that going to be like a name?
That is any name you want. I chose my own just to be
but it doesn't
confusing.
match your GitHub name, Sean Talts.
It could, but it doesn't. Right. It's just it's a name of your choice.
Are you about to show us an example of like doing a git push to like Sean?
I didn't type that in here. I don't think I should have. But the syntax is, so I'm very careful when I push anyway, so I'm always typing git push origin branch name, just to be clear, because if you don't, Git will push everything you have everywhere, which is sometimes fine, often fine, but not great if you've like got local edits to develop for some reason. Right, so so for me it's fairly easy. I just type git push the remote name and then the branch instead of origin I put Sean because I added it as Sean. So it's pretty simple. I think it's a good idea to add that to the slide though. I'll do that.
So that means when you push Sean rather than push the origin, it'll go to Sean Talts math.git.
Yep. Yeah.
Are you usually developing on a checkout of the math library all by itself, or on a checkout of the command stand thing with the recursive stuff?
Usually,
I just don't really know how to use submodules, so
yeah.
Can you like develop on the submodule part?
You
and
can.
push to that
You
as well?
You can, but so the way that I would recommend everyone set up their local stan is to do the git clone recursive of command stan, and then you will have, that will include a clone of stan and a clone of stan math.
Okay, so you have like a whole separate Git repo for math inside it. That's what this
Right,
module does.
right. Yeah, and so there's some weird things that happen as a result of that, but like mostly you probably won't encounter the weird things as long as you use recursive. So then your math repo is essentially just stored under command stan, lib, stan math. and yeah, and that's where you would add this remote to your math fork.
Okay,
Right, and that's where you would branch from math if you were updating branch, and branch from stan if you're updating stan, because like what we're gonna show you later when we go through an example, it has to do both to get everything through.
I was just curious about how big is the community that's currently contributing to STAN? So what's
I didn't include it in the screenshot. Like, there's probably anywhere from 8 to 20 people in our meetings weekly,
okay?
which are over Google Hangouts Thursdays at 11 a.m. Eastern Time, if anyone's interested. That roster kind of rotates a bit. What do we have?
That's not the same as people who are actually submitting.
Yeah,
Pull
I mean,
request?
I can answer this in a couple different ways.
Yeah.
There's over 30 people on our core developer team, but that's spread out in terms of effort to what I've estimated to be about 10 full-time equivalent people cranking along. In terms of like outside submissions, we get lots of outside submissions for doc and for little patches in R. We get like dozens of those things from like dozens of different people. So we try to be friendly and prioritize helping people get their first push through, so we get more developers eventually, because we want to grow. And now it's a lot easier than it used to be because the development's much more modular. It used to be very hard a few years ago because everything was in flux. But things are much more stable now, so it's much easier to bring more developers in. And also we have more tiers of developers, so like Daniel Lee and I don't have to help every new developer through everything. There's much more doc and stuff, so it's easier. But if you try this and find problems, let us know, because we want to keep improving the doc and make it easy for new people.
Yeah. Other questions about remotes? Yeah.
So, because like I don't have access, I can't push to origin on Stan. So
Right.
when I fork, I may not need a remote per se if I push to my local origin.
It depends on how you clone it. Because of all the submodules, it's
Yeah.
quite complicated. If you forked everything, I think actually the forking doesn't change the submodule reference, which is quite annoying. So even if you fork command stan and cloned your own fork of command stan recursively, it would point to like standev stan. That's kind of why I wrote them in this confusing way, because it's submodules suck basically. Yeah.
Yeah, we're going to collapse this across command stan, and math as soon as we get a developer with enough time and patience to push our 3 repos together.
Yeah, the merging the repos is easy. It's the writing the script to migrate the issues and pull requests and like getting buy-in from people to like have them update their own pull requests and stuff like that.
We will make it happen probably during the next year.
Yeah. Other questions? Cool. Right, so this you might recognize this from other open source projects. On your fork, you can create a branch or not. Might be nicer if you made one. Write your code, your tests, and your doc. All of these things are required for pull requests. We have a bunch of checks that will run on Jenkins. It's good if you can run some of them early because it might catch stuff. So CPP lint is a linter that kind of makes sure we follow some rules, and Clang format will kind of automatically format your code to follow a bunch of those rules. Talk more about that later.
You'll talk more about that.
Yeah. You'll add the files, then you will commit with some message about what you were trying to accomplish there. Push to, I should have put the fork name here instead of origin, sorry. This would have been a good example, but it shouldn't be that hard to imagine replacing origin with your name. You'll open a pull request. I'll have some pictures of that later. Branching is fairly easy. You guys seemed familiar with Git. Right, so here's a kind of complicated example where you might be working on kind of one idea that will be split across, in this case, 6 files. It could have been probably 12 if we had been very dogmatic about the split. So you'll see the files split across forward, prim, and rev. There could also be mixed. There could have been R, but here we're just doing scal and mat. I think going forward, I don't want to decide on the spot, but it'd probably be fair to say you could just put everything in Mac since we're going to collapse them anyway. But right now things are kind of split in this fashion. The tests follow kind of a parallel split as well. So here's an example, like some code from one of the tests. This is what they look like. There's a macro, gives the kind of group of tests and then the name of this particular test. And then you just do a bunch of code using your new functions. Yeah?
Yeah, so I got lost. What does it mean, all these files with the same name in different folders?
So because of the way that we split out the source code by autodiff type and by collection type, basically.
Go write the diagram on the board. I've been itching to use the chalk.
Yeah, that'll be good. Because of the way we do this split, the same idea might have different, like this is a metaprogram. So it has template instantiations for reverse mode that are different from its instantiations that are unaware of autodiff or lacking autodiff that are different from the ones for forward mode. And the same for matrices. Like it has special things that it does just for eigenmatrix types versus scalar types. So because of that, this...
That's as high as it goes.
Right. Oh, I see. Okay. So because of that, the same idea might live in 6 to 12 places because the idea has like different implications for different autodiff types and for different collection types. Does that make sense? Yeah.
Yeah, these are the legal includes. So the thing is, if you have something that's primitive that just works on double and ints, it can't include the reverse mode or forward mode autodiff, but the reverse mode autodiff implementation can include, and often does include, the primitive implementation. That's at one level, and same thing with matrices can depend on array types, and array types can depend on scalar types. We're going to remove that second distinction and collapse those, but we're going to keep the top distinction. So this should get a bit easier.
So these are basically alternative implementations of the same functionality.
Different template specializations.
But yeah, the different implementations that differ depending on the type involved. So yeah, so some types, like in prim, we don't know anything about autodiff types at all. So you can't write a specialization for a reverse mode var in prim. Or bad things would happen if you did that. People have done that, but. Other questions on this split or these tests or?
Yeah, this was just to keep our includes untangled. Daniel Lee and I went through about a month between like Stan 1 and Stan 2 because we had all these like super tangled recursive includes just to try to separate our big plate of spaghetti, but we went too far.
Cool. Right, so there's these macros, test and expect equal, that kind of, if you're familiar with unit testing, which is a good question. Who's familiar with unit testing? Most people? Okay, so the basic idea there is that you, the granularity is sort of philosophically arguable, but you would like to test the new things that you're adding or the things that you're changing. And you kind of write code that shows, kind of illustrates the API you're working on and really puts it through its paces to make sure that it does what you think it's doing.
Right, like specifically you want to test all the boundary conditions of things like size 0, integer, double inputs. You want to check all the exception return types and things like that. There's ways to do that. But here there's different types that are important to keep track of. Expect EQ checks exact equality in C++, like bit level equality. Whereas expect float, or if there's, I think it like does the right thing for vectors and things. But expect float EQ tests within arithmetic precision, those things. So that's only testing them up to an arithmetic tolerance, because you almost never want to take two floating point values and do equal on them, because floating point has all kinds of bad properties that make that not work.
We should have a bunch of slides on like numerical computing tidbits, like floating point.
Yeah. I mean, I teach that in Andrew's class every year. I think
Yeah.
we should write it up for the manual.
We could put a couple in here at some point.
And the other thing is that all of those, everything that's in upper the case is a macro from the GTest framework.
Yep.
But it's very difficult to find online a good directory of all the available GTest functions.
Yeah, there's a lot of doc for Google Test, but it's not super well organized,
Yeah.
and I don't think there's a list.
So sometimes you think that there should be a test.
Yeah.
And we have a lot of our own customized tests for things too that are usable that we'll point you to if you start. So before you go down the road of writing thousands of lines of test code for something, ask us. There might be something already there to help.
Because the other thing for the Google Test framework is if you feel like you need to set up kind of mock objects or set up what are those called? The test environments.
The fixtures?
Yeah,
Fixtures? Yeah.
test fixtures.
Yeah.
Hopefully you won't need to do that for adding a simple function. So.
Yeah. Questions? Right, so how do you actually run these things? Unit tests you run with this Python script mentioned earlier. You can give it a flag the J flag, that says how many cores you'd like to use to compile things. And then you give it a bunch of either C++ names or test names or test directories, and it kind of does the right thing and expands that out into the full list of tests and compiles them all and runs them all. CPP lint can be run fairly quickly. Auto formatting, it was my pet project, sorry. Typo. If only we had auto spell checking. So, yeah, so I think there was some time being spent on like back and forth on pull requests about how to format certain things, and we have a style guide, but it's like a diff from another style guide. So Clang format encodes 70% of that and automatically makes your code look like that, which is great. So that runs both on continuous integration, and it will actually commit to your branch. So your branch might have changes if you push and you have a PR open. You can pull and incorporate those. It should, if you pull relatively quickly, it should be very painless. If you install it locally, I think it comes with Mac, but maybe not with other OSs. You can run, there's a Git hook in the hooks directory, or a script that will install the Git hook, and then it will run Clang format on all of the files that you are changing and add those to your commit before you commit. It's very cool. There's more about that at this link.
There's also an Emacs mode.
Oh, right, yeah. That's maybe the most important one. If you have Vim or Emacs, there are modes that follow Clang format, like configuration files, which we have in our repo. So they will automatically do kind of like our style for it, which is great. Oh, here's an example with the correct origin, or the correct remote. So let's say I edited one of these tests. I can add it, write some message, and then push to my remote's name with the branch name that I chose before. And then when you go to make a PR, you might log on to the GitHub website, go to the math repo, and see this notification, which is quite handy. If you've just pushed, even on a fork, it will say, hey, would you like to make a pull request from this branch? And you can just click that button. If you don't see that button, you can click the other button here, the new pull request, and you'll get this slightly more confusing screen where you will need to change your the remote, the head fork on the right, as well as potentially the branch. So here I changed them to look at my fork and look at my descriptive branch name. And then you'll create pull requests. And once you press create pull request, there'll be like a template that's kind of, I didn't include it here because it has been changing recently, but it has a bunch of instructions on like, you should run the unit test probably. You should run CPP lint.
And you need to fill in the license. Right.
License is the most important one. But there's a bunch of other suggestions about like how to describe your issue, what the expected output is, and stuff like that. Or that's for issues. I guess the issues, anyway, there's a bunch of stuff in there that you should read. Right, so how do we actually release Stan? Like what happens to all the code that eventually gets merged into develop? Yeah, the pull request asks for that to happen. Someone will merge at some point, hopefully. we want it to be stable at all times, hence the Jenkins and continuous integration steps. At some point, we will say, hey, it's time to release Stan 219. We'll choose some commit and develop, and we will tag it with a version number, major, minor, patch. Only the major stuff breaks backward compatibility. There's bug fixes. Then we will merge that tag into the master branch. So master will always be, except for a few seconds between creating the first tag and merging, it will always point to the most recent release of Stan. We want to also make sure that that's always stable. And then I think here, are there any questions on this past stuff before I hand it over to Bob? Cool.
Good, that was a little faster than I thought. You get through all this stuff. I think we're scheduled to go like an hour and a half and take a half-hour break and then go another hour and a half. Is that right?
Yeah.
Okay. Conveniently, there's a clock right here, so I guess that means I can go till roughly 10 o'clock and then we'll take a break and come back at 10:30 and then go till noon. Okay. Where's the clicker? Okay, so what I'm going to do in the rest of this is actually go through some examples, and we're going to ramp up the examples from sort of simple all the way up to seeing actually how the normal distribution's actually coded at the gut level with all the template metaprograms in Stan. So this is, as opposed to being a lot of process complication with Git, which always makes my head spin, this is C++ complication, which makes everybody's head spin. So look, I'm going to start by showing you how you actually code a distribution in Stan itself, right? So this is just a program with a functions block. So there's a definition of the normal LPDF, the log probability density function for the normal distribution. We already have normal underscore LPDF built in, so no one would ever do this. I just wanted to choose an easy example. Like I was thinking of doing like the circular Cauchy distribution, and it had all these like hyperbolic tangents and things in the derivative, so I was like, let's just do something. Sean actually convinced me to do something simple here, so we're doing I was channeling for Andrew and wanted like a really complicated example, and then I was like, no, let's do something simple. So this is what you see here is the definition is the log scale density for the univariate normal distribution, right? Here we just have a scalar value for y, mu, and sigma, and they're typed as real in the Stan language. So what I'm going to try to explain to you is how those types in the Stan language break down into our underlying C++ implementation. The basic idea is that any real type in Stan has to be instantiatable as either an autodiff type or a double type or an integer type underlyingly in our math library. So the math library has to cover all the possible instantiations of this thing. We're going to start, though, by letting Stan write the C++. So what happens when you write a function in Stan and then you transpile the Stan program to a C++ program, right? Basically what's going to happen is it's going to generate a C++ version of this function that will actually work in full generality for Stan. Then I just have an example of how we're going to use it. So we're just using this where y is a parameter and the other two things are fixed. The location of 1.5 and the scale parameter of 3.2. Remember, we take scale or standard deviation as the parameter here, like R, so it's not like bugs or a lot of other packages that use variance or precision for a normal, right? So this is just going to sample from that normal. Yeah?
Don't you need a pipe? Or I'm confused.
A pipe?
Yes, of the real y. At some point.
No, not for the variable definitions. I haven't actually got that changed in the language so that when you actually write the function,
Yeah, right.
it just gets written as a straight argument. We should make that syntactic change to make you be able to do that. Can you make a note of that, Metz? Can you make an issue?
I thought we had an issue open on that.
There might be, but I don't think we actually, maybe you already changed it and we support that
No,
now.
I haven't changed it. You're
Okay.
absolutely right.
Questions like this, we just route to Mitzi now because she's working full-time on updating the language. Okay, so what's missing here, right? I guess when we do the unfolding, it just throws all the code up at once. Input validation, right? If we were writing this for real, what we want to do is we want to go through and test that all our arguments are correct, right? We want to test that sigma is actually non-negative and finite, and that all our other values are finite, our location and our actual random variable are finite. And we can use the reject statement in Stan to actually do that. When we see in C++, what's going to happen is those reject statements basically get translated as throwing exceptions. So when things go wrong inside of a Stan C++ program, you throw an exception, right, which is wonderful. If you've been used to working in like C, it's really, really painful to deal with exceptions and return codes and all this propagating stuff, right? We just throw an exception, and then the highest level, or I should say the lowest level function above that that knows how to deal with that exception will deal with it. So if we're doing something like sampling, and one of our log density functions or some function implicated in evaluating our log density throws an exception, we're going to catch that up at the algorithm level, report an informative message to the user, reject that particular state of the sampler, and go on, right? But from the math library perspective, all you need to do is say, hey, I had some kind of problem, throw an exception, and let somebody higher up than me try to deal with it, right? And in the Stan language itself, exceptions are created by this reject statement because they essentially reject the state in all the algorithms. You should not use reject statements to try to constrain parameters, saying something like in the transform parameters block or something, if some transform parameter winds up being less than 0, reject. That will cause Stan to devolve into random walks. You want to make sure everything's continuously differentiable for Stan models. That's another point though. So we're going to implement that in Stan with the reject function. There's a bunch of restrictions, though, on actually writing a function in Stan. So they're not polymorphic. They only work for a single signature, right? So we can't actually write the library function vectorization, which is going to be our final example when we're done, is showing how to write the fully vectorized normal distribution. Right, so we can't overload. I think we figured out how to do that, and after the refactor Mitzi's going to work on, one of the things she's going to do is make sure we can overload, because there's a lot of places we want to do that. We want to write different functions that have the same name, and right now we can do that in the math library, and we can do it in Stan, but we cannot do it with Stan user-defined functions because of the way we generate functors internally. We also don't allow branching on traits. So one of the things that Stan's built-in distribution functions do is they check to see if terms in the log density are constant. That is, they're just double values and don't depend on any parameters. And if so, they drop them from the calculation. That's because our optimization, our sampling, all the algorithms that we use, our variational inference, they only care about the log density up to an additive constant that doesn't depend on the parameters. Right? But we don't have any way in a user-defined Stan function to say, hey, if this thing's constant, just drop it from the calculation. I'll show you how to do that later in the C++. We hope to be able to add something like that. Now I'm going to show you how this works in command Stan. So as Sean hinted, the way we typically work when we're developing new, at least the way I typically work when I'm developing new functionality for Stan or the math libraries, I work up in command Stan. I add things lower down so that I can actually work with models end to end up at the command Stan level. Right? It's nice to see how everything works end to end, and then you break it all down into unit tests and everything appropriately. Right? So we have to CD to wherever we've checked out command Stan. And you can see that I've got this thing instrumented up at the top, the command Stan developed. So we have some instructions on tricks among our developer process stuff in those links up front that will show you how to actually set up your command line so that it tells you which branch you're actually in, right? So we're seeing here that we're pulling, right, from develop, and we're on the develop branch, right? So here I'm actually, all I want to do is run something, so I'm just pulling the latest version of development here, right? And then I can make Stan update. That command is going to make sure that you're using the version of Stan that goes along with the version of command Stan. With submodules, each module that has a submodule says which version of the submodule it's currently using. Right? So the make Stan update makes sure all the submodules are all up to date. So after this, I now have a perfectly up to date with develop version of command Stan, and then I can just use make. I dropped that file, mynormal, into temp2, right? That's the Stan file, mynormal.stan that I wrote here, right? Oh, that's clever. It doesn't actually go backwards. Cool. Doesn't actually. We're just trying out this package for things, so it's funky because it's R. So that make is going to use 5 different processes to make. Make's parallelizable, so if you have multiple cores, it goes a lot faster. So that's going to actually build the whole transpiler. So it's going to build Stan C, the actual executable that maps Stan programs into C++ programs. And then it's going to show you this. It's going to actually be translating the C++ program and so forth, and it will eventually link it, and when you're done, right, that's where the model is, and it's compiled at optimization level 0. That's with the O equals 0. That just makes compilation a lot faster. The models will run about 10 times or even 20 times more slowly without optimization, because we lean very heavily on the C++ optimizing compiler with all the template metaprogramming we're doing. But when you're just testing things, usually you're using very simple models that run very fast, and you don't want to wait 45 seconds or 30 seconds for a compilation. Compiling at optimization level 0 will cut the compilation time down about half because it doesn't do all the optimization, right? And it tells you where it actually outputs things. So you can see what the actual HPP file is, mynormal.hpp down here. That's the thing that's actually produced. That's the Stan model class code. So you can go look at that and see what it actually looks like. We'll look at a little bit of it as we go along here. Then sampling from the posterior, I just CD over to the directory I'm in, and then I can run the name of my model as an executable. So it's ./mynormal. That just runs that function, right? Or you can make the thing executable or something and do it a little more easily. Sample tells you want to sample, and here I'm going to do 10,000 samples. That is, I'm going to do a sample size of 10,000, do 10,000 draws after warm-up, and it will take the default number of warm-up draws as 1,000. I wanted to do this so that we could get the answer very precisely, so I could show you that it's actually working, so there wouldn't be any questions here about. It first dumps out all the config that it uses, right? And it writes the output to output.csv as a regular CSV file. With the header corresponds to the parameters, and the rows are just the values, right? And then we can run Stan summary. So there's an executable Stan summary that gets built as part of building Stan. So if you do command Stan bin Stan summary, so remember command Stan is just where I check command Stan out. I just put it right at my top level namespace because I work there all the time. And then it shows you the inference for the model. I rearranged things and I compressed it a little bit so it would fit here. It's not quite as pretty as R, but it's more consistent than R's output. We also, by default, dump out more things about the sampler, but this isn't really about the sampling. But you can see the posterior mean is 1.5, and the posterior standard deviation is 3.2, so we're getting the right answer from our sampling here. You can check the intervals are right as well if you want. Right, so, and all of our convergence monitoring's fine, so. That's how you do something if you want to write a function in Stan, right? But that's not particularly an efficient way and not a particularly general way of writing things. Turns out there's a whole bunch of different approaches you can take to writing things in C++, and I'm going to summarize them, and then we're going to go through examples of all of them. So the first thing we could do is we can just independently template all the scalars that are implicated in our program. Right? This is going to use automatic differentiation to take the partials of all the outputs of our function with respect to the inputs. So when we're doing automatic differentiation, the key thing we need to know for every function we're implementing, the function's going to have some outputs and it's going to have some inputs. We need to know the derivatives of the output with respect to the input. We need all of those partials of the result with respect to the operands, right? If we just template all the scalars, which I'm going to do for the first example, what's going to happen is the Stan math library will use autodiff itself to compute all these. This is a very easy way to write a function into C++, but it's not very efficient, right? It's actually the technique that's used for functions that are defined in the Stan language. If you look at the code that gets generated for those, this is the technique that gets used. The nice part about it is it works for any order of autodiff, reverse, forward, mixed, and as Sean said, Ben Bales, we have this fantastic intern this summer who's just cranking through code, and he's finally, after like 2 years, cracked the problem of how we're going to test our higher order auto diff. So I'm really psyched. We're going to be able to launch Riemannian HMC, and we're going to be able to do like effectively Hessian calculations for maximum likelihood and Laplace approximation. So it's going to be great. It uses traits to determine intermediate and return types. I'll show you how that works. There's a lot of metaprogramming involved in Stan. Right here we're going to use traits metaprogramming to figure out what the return types are. The second thing you can do is you can implement a custom variable implementation. This is our reverse mode autodiff implementation type, and you can actually just go right to the guts, get your hands on the lowest level possible machinery. And this is the most efficient and customizable option. You can do things like lazily evaluate the partials on the way back, which is how Stan saves a lot of memory compared to other autodiff systems. But it only works for reverse mode. So if you use this mode and you want to write a function in Stan, you'll also need to write the templated mode, so it'll work with scalar, like regular primitives, and it'll work with forward mode autodiff types. Right. We also have a couple helper implementations that will let you pretty easily write functions without having to get involved in our really low-level implementations of our autodiff type. One is this pre-computed gradient structure. What this does is it computes and stores the full Jacobian of your function, right? If your function has a lot of outputs, you need the derivative of each output with respect to each input, which is the Jacobian. So you do that using double calculations on the forward pass. It's still only reverse mode, so it still needs the templated version. But that can be very efficient. It doesn't give you quite as much customizability, and it actually requires you to allocate the memory for the full Jacobian. And the fourth approach is the operands and partials. This is what we use to implement our densities. One thing I'm not telling you about here, because it hasn't been merged into develop yet, is the thing Ben Bales has been working on. We now have a fifth way of writing this, which is going to be the most efficient thing to do for multivariate output functions, which lets you just write a very simple adjoint Jacobian product functor all in doubles. This will be great for writing higher order, for writing functions that take multivariate output. But it's much more complicated than what we're going to be able to get into today. But if you're really interested in writing functions and you want to write matrix functions, for instance, because we could really use some help making our matrix derivatives better, then you want to look at that adjoint Jacobian apply. There's documentation for it. There's examples for it. It's been merged with develop, but it isn't merged into Stan yet. What I will go over, though, is the operands and partial structure. This is basically a custom tool for vectorized log densities that involves a ton, but we can use it for any single output function that you want to vectorize. It works for any order autodiff, which is really cool. This is like the first thing Sean did when he joined the project, was generalize our operands and partials so that it actually worked the way we wanted it to, which is cool. This is the output. Remember that function that we wrote in Stan? This is what the Stan C++ transpiler does. This is the code that Stan produces for that simple implementation of my normal that we saw. So it's heavily templated and it's pretty complicated. I've reformatted it a bit here so it's a little more readable than the actual output, although Mitzi's working on making the output a lot more readable. It's got all these template types, one for each of the arguments. It's got this traits metaprogram to calculate the return type. It's got all kinds of, utility definitions. The last argument is a print stream. The reason we need that is because Stan functions can have print statements inside of them. And if my normal had a print statement inside of it, that print statement would be writing its output to that stream that gets passed in. Right? So we're defining a bunch of utility things. The dummy vars are there to fill in default values efficiently. And you'll see that everything's instrumented with static statement position. So there's all this current statement begin thing that's going on, and we're just going through and we're actually updating where that's actually happening. So each thing that happens gets updated with where you are in the underlying source file. Then this try catch lets us throw exceptions that can use this rethrow located method to actually tell you what line number you've got the exception in. So this is all super complicated, But none of this boilerplate is going to be necessary when we write our own functions like this, because they're not going to have print statements inside of them, and they're not going to have all this need to throw located statement instructions.
So I have, maybe it's a very basic question, but I don't really know what do you mean by reverse and forward pass when you do the auto diff.
Oh, there's two different kinds of, I actually have some slides that'll go over how the basic autodiff works. Reverse mode autodiff, so we have two different kinds of autodiff. Reverse mode autodiff is for computing gradients efficiently, and we have forward mode autodiff, which converts, which is a way of computing all of the derivatives. It's computing multivariate output derivatives with respect to a single input. We can put those things together. We can nest reverse mode inside of forward mode to compute second order derivatives, and we can nest reverse mode inside of forward mode to compute third order derivatives. So it's just different systems for computing derivatives under the hood. Right? The only one that I'm going to talk about is the reverse mode, because that's the only one we're actually using in any of our algorithms right now. And I'll go through a bit about how that works, how the two passes of that work. Because it's relevant for writing these functions. You're going to need to know how that works a little bit in order to write the derivatives. Right? So now let's talk about a C++ implementation that has a templated scalar. Right? So you can see the signature down here. We're just going to template the single argument y in writing, and we're going to have a return type of t. So it's just and this avoids having to use all the traits metaprograms. The next thing I'm going to do is show you how to generalize this. So y can be an autodiff variable, but we're assuming mu and sigma are just real values. So this isn't sufficient for actually implementing a stand function. This is deficient. It's just an example that's giving you some scaffolding to get to the program. So all of our non-primitive parameters, like this constant t or it may be instantiated as a primitive, but they're all passed by constant reference. Inside of stan, all values, like in stan, when stan passes an argument to a function, it's always passed, if it's a primitive, it's passed by value. If it's an autodiff variable, it's passed by constant reference. And if it's templated, primitive, it's passed by constant reference. The compiler's good at unfolding all of this stuff for us. The return type, t, is the same as the templated argument type. That means we can instantiate y to be either an autodiff type, or we can instantiate it to be a double, or we can instantiate it to be an integer, right? So it gives us flexibility in that argument that we want to take derivatives with respect to, right? So what's the C++ code look like? This is the full implementation of this. Again, it's not quite ready for Stan yet, but this will do the trick for the model. That is, this we can use as a drop-in replacement for the my-normal that I implemented in Stan. Right? So it's much simpler to implement it in C++ because we don't need all this boilerplate stuff. Right? So one thing I want to talk about, because it's really important for the way we do things, is you'll see that there's a log function there, log sigma. Right? What's going to happen is we're going to use all of our usage is going to be like this. We're going to have a using statement for the standard version that's going to bring into the name resolution space the standard version of log, the log that comes from the standard library. So that becomes a candidate for any usage of the function log within scope, right? And we only allow using statements, I thought I said that. Yeah, we only allow using statements inside of scopes like this. You cannot put a using statement up at namespace scope. Don't do that. Very bad practice. Right? But then what happens if sigma is an autodiff type, which isn't going to happen here, but it's going to happen in the more general case, right? We haven't explicitly brought in stan math log, which is the version of log we need to apply to our autodiff types. But what's going to happen is, so that's going to be stan math var, because that's our autodiff type, and I'll explain how those work next. Those work through argument-dependent lookup. So argument-dependent lookup is a name resolution technique in C++ that says if the argument to a function is of a user-defined type defined in a namespace, then go look in that namespace for an implementation of the function. So if we pass in a stan math var, Argument-dependent lookup will go find stand-math-log to apply to it, so we don't have to do that. We don't have to hard code everything. You see this pattern all over templated C++ code, right? So I just wanted to call it out here. It's a lot of these concepts in C++ are complicated when you first see them.
So the main thing you're saying here, that log might be the standard log if it's double, but it won't be.
Yes. Otherwise, it'll go find the one in our namespace. Yeah.
Can you comment on an efficiency gain by knowing that it's a double and using the standard log versus the ADL log from Stan?
The double version is much more efficient because what's going to happen, as I'm about to show you soon, is that when you actually use the Stan version, we actually create a fairly big data structure, push it onto a stack. So there's memory implications and there's autodiff implementations because we actually build up the whole expression graph so that we can propagate derivatives. So there's memory overhead and sort of interpreted virtual function call overhead, right? So we want to use the double versions when we can and not over promote things up to vars. It's legal to just cast everything up to vars. We have an implicit constructor that constructs a var out of a double and everything will work that way, it just won't be efficient.
When you write the function in Stan, does it know which log to use? Or
Yes.
Yes.
Yes. Yeah, because it does the same thing, argument-dependent lookup. So when you go here and look at this, that sigma can be just about anything here. This is one of the reasons why code coverage is very hard to do for a template library because you don't know what the possible template instantiations are. And like one of the big issues we have in testing is making sure we instantiate our functions with enough templates to test them. But here, when this log down here happens, right, that log sigma, oh, I guess that gets generated as Stan math log sigma. Interesting. Maybe we wrote a Stan math log that'll work for that. We must have, because otherwise this wouldn't compile. We had a lot of problems with the C99 namespaces across Clang, Microsoft, and G++ because they all brought them in differently and we were getting tons of name conflicts and we eventually went and threw definitions of almost everything into the Stan namespace, which we have to be careful about not causing conflicts on. Okay, so let's see how this actually works. So this is, we can take this function and just evaluate whether it works to do what we want by using our autodiff. So here's a complete skeleton for this. There's some elided parts here where it says my normal implementation here. The idea is that's where you put this code, right? So it's a main function, and what it's going to do is it's going to create an independent variable for y, which is an autodiff type. It's going to create constants for mu and sigma, and then it's going to define another autodiff type LP that's the application of that function my normal. Then it's going to call the gradient function, what that's on the result. So LP is the final result of this function. LP.grad says compute all the derivatives all the way down. Then what we can get is each one of these variables is going to have an adjoint. So we can look at y's adjoint value. That's going to be the derivative of the value with respect to y, right? So this is what autodiff does for us, right? We actually get the derivatives of these things automatically. Right? So we need some includes and a main, so you can see what happens when it actually runs. Right? We have to compile it. We're compiling it, and I think I've got all these things in here. Right? It goes in mynormal.cpp, and we compile it with Clang. We're using the C++1y standard because that matches what R is using. We're kind of bound to do what R tools does to make it easy on Windows and R users and binary compatible, but they're about to update their C++ compiler, so we'll be able to open up much more of the C++ 17 functionality going forward in probably about 6 to 9 months. But we're also happy that we just opened C++ 11 functionality, that we're still like kids with new toys running around fixing everything. A lot of libraries that you need to bring in to actually compile this. You need to bring in the math library, the eigen library for matrix functionality, the boost library, which contains a lot of our template metaprogramming stuff and a lot of probability functions, random number generators, that kind of thing. Sundials, which contains our ordinary differential equation solvers, and in the end, the file that you actually want to compile. right? You could send it somewhere else. I just let it go to a.out, the standard default output. Then when we run it, we get the value, and we get the value for the derivative. And you can go back and figure out that that's right. I'll show you how to do that in a second. Right, so that's just crudely using our auto diff at a very low level. Right, you're not going to have to use the auto diff at this level for anything you do. Maybe you'll use it in testing, but probably not even there. I just wanted to show you basically how it worked. So here's how we can implement that same function with more flexible template types. This is actually a Stan appropriate implementation of this function. It's just a simplified version of what Stan itself outputs. Right? So if you look at Stan's output, it looks very much like that. Right? Here we're going to get promote args. It's going to look a little different than that in ways I'll tell you later. Ty, T mu, T sigma. So we've got a separate template parameter for each one of our arguments. That's to address the efficiency issue that came up earlier, so that we can have, say, mu come in as a double, sigma come in as a double, and y come in as a parameter or a random variable, or vice versa. Very often when we're doing estimation, mu and sigma are unknown, and y is actually known as data. Right? So we're going to have the same, using standard log, we're going to have exactly the same return type. The only thing that's different is we have this traits metaprogram up here that's calculating what the return type is. Right? So it's not common, by the way, to find libraries that have everything templated, which is why we had to do so much of our own matrix library and our own density library stuff. Question?
So that looks like a standard boost library.
Yeah, it is. It's actually calling a boost library function.
It doesn't do anything Stan specific, right?
What that's doing is I think I've got a slide right here. So promote args computes the maximum value of its template types, where integers less than, it's actually integer automatically gets promoted to double. The minimum type this thing's going to return is double. And integers less than double, doubles less than var. So if there's any var arguments, the return type's going to be var. If all the inputs are integer or double, the return type's going to be double. Right? And that's a standard built-in. I think it may even be built into C++ 11 now, because they took a lot of the boost trait functionality and just built it into C++ 11.
So it finds the least general.
Exactly.
type that-
Least upper bound. Yep. Yeah. Yeah, and if you throw in two user-defined types, I think it chokes unless one can be assignable. So the ordering is assignability. So here you can assign a double to a var in Stan, but you can't assign a var to a double. So it finds the most general type that all the types can be assigned to, is what it's actually doing.
Yeah. You might cover it, but what if I want to use the standard log for 2 times pi and the Stan log for, again, sigma? In this
That will automatically do that by argument dependent lookup.
Oh, I see.
Right, that happens for free. So it will see the double value. So what happens is it brings in, when you're trying to resolve a function in C++, it brings in all the candidates. That means all the overloads and all the base templates. And it has to find a most specific match. So the match in the standard library will be tighter than the match of the var, so it won't need to actually do a promotion of a double to var, so it will match that.
Okay.
But you could have actually written standard : log 2 pi there with no loss of generality, because you know those are constants. Pi is a function that returns a double in Stan for pi's value. Right? The other thing to note here is arithmetic operators in C++ are left associative. So this actually adds the double value to the T sigma type. So on the right here, I've written the type of the term. So that minus 0.5 times log 2 pi, that's a double value. Minus 2 times log sigma is going to be whatever the type of sigma is. If that's double, it'll be double. If it's var, it'll be var. Then when we do the subtraction of the first term from the second term, the result's going to be T sigma. So it's not going to get promoted to double. If we had done this the other way, associated the other way around, it would be less efficient, because we may promote when we don't actually need to. It's a fairly subtle point. The third term actually involves all of the types, right? So that's going to be the most generally assignable type out of all of them. And I'll show how this gets exploited. The reason I wanted to bring it up here is we're going to exploit this later with template types to drop constant terms. So we're going to be able to, in the more sophisticated implementation, say, forget about that minus 2 log sigma term if sigma is a constant. We don't need it. Right? So now I want to take a digression into how autodiff works, and hopefully I'll be able to finish this up before the break, and then we can come back and do more complicated examples. We really had no idea how long this is going to take. I still don't know how long the rest of this is going to take. So I'm just going to be telling you about reverse mode autodiff. And what reverse mode autodiff is actually takes 2 passes. It takes a forward pass, and in the forward pass it builds up a directed acyclic expression graph. Each node is a sub-expression. Where is that? I think it should be. Oh, my image didn't show up. What the hell? That's bad. I think I have another version of this presentation where it will show up. Nope. Man, oh man. I don't know how that got lost. Anyway, that thing was the autodiff tree. Let me just write what it was. So that's going to be something like a minus sign, and then it's going to have something like subtraction. This is going to be a log. Right, and this is going to connect to sigma. Well, really, it's going to be a minus, and then it's going to connect to a log. Right, because what we're doing is we're computing negative log sigma. Sigma is an input. Right, we compute the log of sigma, and the final term's a negative. And this is going to be a square term here, and then it's going to be a division. Right, and it's going to be a division of a subtraction of y and mu, right, divided by sigma. Right. So this is the expression graph that we get for the thing. We have 3 inputs, y, mu, and sigma, and we do y minus mu divided by sigma squared. Well, really, there's a negative 0.5 times here, too. Sorry, I had this in a slide, but it got lost. Right, so it's minus 0.5 times the square of this minus log of sigma there.
It says it should be an acyclic graph, but you have a cycle there.
No, sorry, this is the top. Let me draw the arrows in. There's no cycle.
Going to sigma.
It's not a cycle. A cycle is you can go around and come back to where you started, so it can share. In fact, that sharing is really important, because what's going to happen is if there was more expression graph down here, right, if the sigma wasn't an input, it actually had to be calculated. What's going to happen is this is going to automatically give you what's called a dynamic programming algorithm that's going to only calculate this thing once. You have a problem if you're doing something like symbolic derivatives like PyMC3 does. You get a lot of advantages from doing that, but you get some disadvantages, which it's very hard to share terms in that kind of thing, right? Whereas doing this kind of adjoint calculation just sort of automatically gives you like efficient sub-expression derivatives from the reentrancy into the graph. But there aren't any cycles, and that's important because as you evaluate, these things go on a stack. So in the forward pass, what happens is the first thing we evaluate is y minus mu. We create this node. So this is the first thing that gets created, the second thing that gets created, the third thing that gets created, the fourth thing that gets created, the fifth thing that gets created, the sixth thing, seventh, eighth. Oh, I guess this is 7, 8, 9, and then, well, no, sorry. This is all numbered on the slides that we're missing here, 9, 10, and 11. Right, so this stuff's all going to go on a stack in the order that it's evaluated. If you know computer science data structures, it's basically going to do a topological ordering of the stack such that every node in the stack has every one of the things it depends on below it. This is going to be important for automatic derivatives that we have. right? So what we do in the first pass, in the forward pass, is we build up this expression graph. That's the core to AutoDiff, is building up this expression graph, right? And then we calculate the adjoint for each node in the reverse pass. So the idea is that for each operand we have, we're going to take the adjoint value and we're going to add the adjoint of the parent node times the partial, right? So the idea is that we have some kind of result here, right? And we're going to have some kind of operand 1 and then operand n over here. And each one of those is going to have a partial here, right? And that's going to be the partial of this result with respect to this input. And each one of these nodes is going to represent a sub-expression like this. And each one of these nodes is going to have an adjoint value and a value. The adjoint represents the derivative of the result with respect to that node, right? And this is just passing the chain rule. So what we do is we take the derivative here, right? We've got some top level result up here. This adjoint value is going to be the derivative of the result with respect to this node. To get the derivative with respect to this node, we take the derivative of this node, multiply it by the partial, and add it down here, just like that.
So the final result is always like a scalar.
Mm-hmm.
Okay.
Yeah. I guess I probably should have showed you the data structures for these things first.
You actually show the image that you have. You just have to right click on it and say display image.
Oh, really?
Well, it's apparently an encapsulated postscript as my doesn't show.
Oh.
It worked for me, so.
Open image?
Yeah.
Oh, I will, but I'm in full screen, so I see. Ah, there we go. Much prettier. I guess I got it pretty close. Right, so this thing gets built up this way. I guess I used power 2 instead of square there. Right, and you can see the constants in gray. So each of these nodes get built up, and they get built up in the order they get visited in that expression. Right, and here it's clearer that things are acyclic. So then what happens is you start at the very top. You assign and each one of these things is going to have a value and it's going to have an adjoint. And you start at the top by assigning the adjoint of the final result, that node in red, to be 1, because the derivative of the result with respect to itself is 1. And then you just keep propagating the chain rule down by multiplying the derivative times the partial and adding it to the daughter.
Just out of curiosity, I mean, I've learned about backpropagation. Is that basically this? Or
Yes, backpropagation is a simple case of this. This is like the more general form of backpropagation.
in which sense is backpropagation simple?
It's only, backpropagation as it's used in most neural networks is just doing this for a particular form, right? They're typically just doing it for logistic activation functions. Right, whereas this is like general. We can do arbitrary like matrix operations and things. So it's much more like what TensorFlow is doing, right? Like TensorFlow it's actually more like what PyTorch is doing. TensorFlow builds static expression graphs, whereas we build them dynamically, right? But it's basically, this is the generalization of backpropagation. You can take a neural network, code it up in Stan, and the AutoDiff will correspond exactly to backpropagation. Like this has been known in this literature for like 20 years, so the connections are all over the literature. You wouldn't know it from a lot of the tutorials, but like AutoDiffs, because AutoDiff was pretty obscure until about 5 or 6 years ago. So we probably wouldn't have written our own had we started this project now. We would have just jumped onto somebody else's project. But when we started Stan, all the AutoDiff libraries were really in bad shape like 6 years ago, so we really had to write our own because there wasn't anything that dealt with memory efficiently enough or was general enough for us. Because generally, it's not the kind of thing you want to like write for your sampling project. Okay, so I said that, and then for each node and from the root, you go and update the adjoint. And then the gradient of the final function is just the adjoints of the input, right? The neat thing about this is that the time and complexity of calculating the gradient is proportional to the number of edges in this graph, right? So the point is that we can calculate a function and its derivatives in a fairly small multiple of calculating the function itself. Usually a factor of 2 to 8, depending on what's actually going on. Some of the matrix operations scale a little less efficiently, and we haven't got all the memory locality worked out. We have an archive paper on this that sort of shows the relative efficiency of a lot of operations of both us compared to other autodiff libraries. So Stan's low-level autodiff is still faster, as far as I know, than things like TensorFlow and PyTorch and everything else. And now that we're going up to having MPI and GPU support, it's not going to be nearly as flexible in something like TensorFlow, but we're going to be able to scale up some of our models at least to the kind of speeds they can get from parallelism. But our low-level library is implemented very, very tightly and very specifically for the kind of models we care about. So we've put a lot more effort into the kinds of things that I'm going to show you for log densities. I mean, I was just out in California visiting all the people who are building this stuff. So they will catch up. They know how to do this. They just need to put in the couple years of programming effort to do this. It's like there's nothing magic that we're doing. We just got a 5 or 6 year head start. So. Plus the cost of partial derivatives, which is usually constant. The slowness of doing reverse mode autodiff, the reason it's not just like a factor of 2 always, is that basically when we do this reverse mode pass, right, and we're propagating the adjoints, all these things are interpreted, right? What's happening is, I'll show you the, we have virtual function calls and memory non-locality. So we've got the 2 worst possible things for efficiency. The thing you need to do to write efficient modern code is you need to make sure you have memory locality, so whenever you're dealing with data, it can all get paged in at once. It's really slow to bring data from RAM into the CPU. It costs 30 or 40 times the cost of an arithmetic operation if there's a cache miss, and you need to go out to RAM and pull something in. That happens when your memory isn't all packed together. So this is, memory non-locality is really bad. Right? The other thing that's really important for writing efficient modern code is branch point prediction. CPUs, the way they run, evaluate ahead of where your program's actually at by trying to guess which branch is going to get executed. If they guess right, it's great. You just keep flowing. Right? If they guess wrong, you've got to undo things, go back, and again, the cost is like 20, 30 floating point operations for a missed branch point prediction. Right, so you can, by these 2 things together, can lead to like huge overhead compared to like writing tight static code. So a lot of what we do is trying to move these virtual function calls, these memory locality calls inside of our autodiff, which is one of the reasons why the thing that Ben just wrote, this adjoint Jacobian thing, is so nice. I thought I had the data types, but I guess I'm going to cover those in the next bit, which is great because we should take a break now. So we're coming back at 10:30, I guess, right?